So I initially thought I'd make a video to introduce beginners to deep learning, but I figured that the resources that I used were already pretty decent enough and that making another video on this topic would be an unnecessary reiteration of information. So if you're a beginner who's interested in this field of I strongly recommend reading Michael Nielsen's online book. At first glance, it might seem intimidating because of all the math that's involved, but the book is structured in such a way that'll give you a thorough understanding by guiding you through this step-by-step thinking process so that you will be able to wrap your head around how a neural network model works and how you can train one. There are some math concepts that you need to familiarize yourself with while reading. One of them is multivariable calculus. Now, don't let that scare you because it's not as bad as it might seem. When I started reading this in sophomore year, I hadn't even taken a calculus course yet, but as far as I remember, all I really needed was a basic intuition for derivatives, which you can acquire by watching the first few videos of 3 Blue 1 Brown's Essence of Calculus series. You don't even need to memorize a cheat sheet of derivatives, just understand what the derivative of a function will tell you. Once you get the intuition for derivatives, you can carry that over to partial derivatives, and that will help you better understand what a gradient vector is. You also need to know some linear algebra. For this concept, you can get an intuition by watching 3 Blue 1 Brown's Essence of Linear Algebra series. But you do also need some practice with matrix and vector operations, and for that, there's a whole series on Khan Academy with practice problems so that you can get comfortable with the calculations. There are of course some YouTube videos on AI out there, and those can be really helpful. 3 Blue 1 Brown has his deep learning series, and Sebastian Lag, or Lage, whichever, has his neural network series. However, these videos are more supplemental, and so if you're just starting out, I recommend that you focus primarily on the online book and you can watch the videos on the side. Before I undertook this project, I read the first 2 chapters of the book, but to understand this video, you just need to master chapter 1. However, because chapter 1 is kind of long, for the purposes of this video, I'm going to try to summarize it in under 30 seconds. So a neural network, sometimes called a classifier, will take in data as a single vector and then produce an output in the form of another vector based on that data. A cost function is used to measure how poorly that network performs by comparing its output with the output that's desired. When you train a network, you are essentially trying to decrease the value of the cost function to a local minimum to increase its accuracy. And that's done with the help of the gradient vector of the cost function. Further details reside in Nielsen's book, and there's even Python code which you can look through. The training algorithm that was used was backpropagation, which is explained in detail in chapter 2. So if you want to understand its code implementation, you can read that. Otherwise, just know that backpropagation is used to compute the gradient of the cost function. The first chapter walks you through how to use the code to create and train a neural network that can recognize handwritten digits. I made a couple tweaks to the code to make it Python 3 compatible, but that turned out to be unnecessary work on my end because a link to the Python 3 version of the code was already available on Michael Nielsen's GitHub page, but at least the whole experience forced me to examine the code in more detail. Nielsen also suggested implementing a fully matrix-based approach, which I did, and this made training 3 times faster. And with that, I was able to get a neural network to recognize handwritten digits with 96% accuracy. I was really excited about this and wanted to develop my own personal project with this code. So I decided to make an application that would automatically open YouTube up for me whenever it detected the hand sign for the letter Y through my laptop's camera. Now, for some of you who have experience in this field, will think that I should use a convolutional neural network since this is basically image recognition. However, I don't completely understand how those work, and this might sound like I'm being stubborn and unwilling to learn, but I promise that's not the case. I will eventually learn it and hopefully do a video on it sometime in the future. But for now, I just want to try to push the limits of the basic feed-forward network. I used the code from Michael Nielsen's book to create and train a network. But to train the network, I actually need training data. On top of that, I wanted test data to measure the accuracy of the model over the training period, which is divided into epochs, or epochs depending on your preference of pronunciation. To do those things, I wrote two Python scripts which both work in a similar fashion. Basically, with the help of the OpenCV library, I can feed frames through my webcam and store the data as a pickle file for later access. Each dataset needs positive data, which are images containing the hand sign for y, and negative data, which don't. Because you're feeding all pixel values as input for the network, it's necessary to grayscale the image so that each pixel is represented by a single number indicating its brightness, rather than 3 RGB values per pixel. It could still work for colorized images, but it's not necessary because think of this. If I make the hand sign for y and I grayscale the image, it's still possible to make out, and therefore a neural network should be capable of the same task. I also downsized each frame to 320 by 240 pixels to shrink the amount of pixel data that has to be processed. In the beginning, I had 4,000 training images and 3,000 test images, and each dataset contained an equal number of positive and negative frames. When I started training, the network correctly classified around 2,000 out of the 3,000 test images. That was still far from perfect, but it seemed to be doing better than random guessing, which indicated that this could work. However, the accuracy didn't improve much afterwards, so I decided to add more training data. But because having thousands of images stored in a Python list takes up a lot of memory, I shrunk each frame down to 160 by 120 pixels, and then collected 10,000 new training images and 3,000 new test images with the smaller dimensions. With that, I got around 2,200 test images to be classified correctly, which is better, but still unsatisfying. So I tried putting each frame through an edge detection filter, hoping that finding the outline of a hand sign would be easier. But the accuracy fluctuated widely over the training period, so I suspected that I set the learning rate too high. When the network is trying to decrease the value of its cost function to a local minimum, it does so by stepping in the direction of descent. The learning rate controls how big each step should be, and if it's too high, then you run the risk of overshooting the minimum. Decreasing the learning rate resulted in a steadier increase in accuracy over the training period. However, improvements plateaued around 1,700 out of 3,000, which leads us to a problem with the local minimum. Sometimes the network can settle at a local minimum that's still pretty large, and in this situation, you'd want to overshoot to find a different minimum. I looked up how to overcome this, and I found a Quora post that suggested applying an exponential decay to the learning rate. This would allow the learning rate to be large at the start of training and then decrease over time. I modified the code to implement this and then ran the trainer, but I only got an accuracy of 1,900 out of 3,000. At this point, I was getting kind of frustrated and unsure of what to do next, but seeing that the edge detection gave no improvements, I decided to switch back to using plain grayscale images. This time I decided to take a more systematic training approach by saving the network object that performed the best during each training session as a pickle and then retraining that network in a later session with a lower initial learning rate. I started the first training session with a learning rate of 2.0, and this yielded a network with 75% accuracy. A second session retrained that network with an initial learning rate of 1.0, and this yielded a network with 82% accuracy. This is still not perfect, but pretty decent at this point. I tried retraining for a third time, but this gave a tiny 0.7% improvement, so I stopped there. I was pretty happy with 82%, but I wanted to see how much further I could push this. So I decided to see how accurately the network would perform on the actual training dataset. So I wrote a small script that would count the number of images that were incorrectly classified from the training dataset and I ran it. Surprisingly, there were only 153 of those images. Some quick mental math revealed that this is close to 99% accuracy. I was very confused and I didn't understand why there was such a big difference, so I googled the problem and I found a solution on Stack Overflow. It turns out that there's this thing called overfitting. Basically, the network is bad at making generalizations about the training data that can be carried over to the test data. Therefore, if a test image differs even slightly from the training images, the network will be unable to classify it correctly. This is especially problematic during training because the network thinks it's getting better when in reality it could be getting progressively worse. You can deal with this issue by adding more training data or reducing the complexity of the model. There are also various techniques that are available to accomplish this goal, such as L1 and L2 regularization, dropout, and ensemble. In the future, I might experiment with some of these to tackle this issue, but for now, that's all I have for this project. I know the results are sort of disappointing, and I'm sorry about that, but I promise I'll continue to work on this and keep you guys updated. I'll try to post a follow-up video before the end of the year, which I know seems like a long time away, but I really want to work on some other projects in the meantime. If you guys want to play around with the code, I've uploaded that on GitHub, which I'll provide a link to in the description. If any of you have tips for me, please do share them in the comments section. But that's it for me. Thank you for watching. Feel free to like and subscribe, and I'll see you next time.